Okay, so we're going to do a few more examples of implicit differentiation, and then we'll try to see how we can use these for derivatives of other types of functions as well. So first, let's try to use implicit differentiation to find the derivative of this equation here. So to find dy dx for x cubed plus 4y squared plus 2x plus 7y equals y cubed plus 6x squared. So remember, in the last video, we found that if you're taking the derivative of an implicit equation written with x's and y's all jumbled together, then we're still going to take the derivative with respect to x on both sides. But we have to keep in mind this rule where anytime you take the derivative of a y term, like here, or here, or here, you're going to take the derivative with respect to y, and then you'll multiply it by dy dx. All right, so let's see what happens here. So I'm going to go term by term and take the derivative with respect to x and use that rule. All right, so the derivative with respect to x of x cubed is just 3x squared plus, okay, here's where things get complicated because we're taking the derivative of a y term. So we take the derivative with respect to y. That's going to be 8y to the 1 power. But because I've taken the derivative of a y term, I also have to multiply by dy dx. Okay, then we take the derivative of 2x with respect to x. That's just 2. Then we take the derivative of 7y with respect to x. Okay, since this is a y term, we take the derivative with respect to y. Derivative of 7y would be 7. But then we multiply by dy dx. So that's our left-hand side of the equation. And on the right-hand side of the equation, we do the same thing. The derivative with respect to x of y cubed would be the derivative with respect to y. That's 3y squared times dy dx. And finally, the derivative of 6x squared is just 12x. Right, that's what we do when we do implicit differentiation. Take the derivative with respect to x, but anytime you take the derivative of a y term, you take the derivative with respect to y multiplied by dy dx. And from here, it's just a matter of solving for dy dx, getting all the dy dx's together on one side of the equation. Now, I hate writing dy dx over and over again, so just for simplicity's sake, anytime you see dy dx, instead of writing it out like that, I'm just going to write y prime because it makes my life a little bit easier. I'm going to rewrite this whole thing as 3x squared plus 8y times y prime plus 2 plus 7y prime is equal to 3y squared times y prime plus 12x. Right, no real, you don't have to do that. I just prefer the y primes to the dy dx's, and in the future, that's how I'll write it instead of writing dy dx every time. Okay, now what we need to do is solve for y prime. And we can do that by moving all y prime terms to the left-hand side of the equation and every other term to the right-hand side. Okay, so essentially what we're doing is we're leaving 8y y prime and 7y prime on the left-hand side, but moving our other two terms that don't have a y prime over to the right. Then on the right-hand side, we can leave the 12x alone, but we have to move 3y squared y prime over to the left. All right, so rearrange this equation by subtracting as needed. And so in the end, what you should have on the left-hand side is you should have 8 times y prime. You should have 7y prime. And then you should also have this term from the right-hand side, but to move it over, we would subtract 3y squared y prime on both sides. So on the left, we'll end up with 3y squared y prime on the left-hand side. Right, in other words, we subtracted 3y squared y prime on both sides. Okay. Now we also need to rewrite our other side of the equation. So we had a 12x on the right-hand side to begin with. That'll stay there. But then I also need to move my terms from that didn't have a y prime from the left-hand side. So I would need to subtract 3x squared on both sides of the equation, and I would need to subtract 2 on both sides of the equation. So on the right-hand side, I'll also have a negative 3x squared term and a negative 2. Okay. Right, so rearranging, right, doing this step here leaves us with 8y prime plus 7y prime minus 3y squared y prime is equal to 12x minus 3x squared minus 2. Now, factor out the y prime and divide by what's left over to get y prime by itself. All right, so what happens there? If we factor out a y prime on the left-hand side, we'll have y prime times 8y plus 7 minus 3y squared. And on the right-hand side, I still have 12x minus 3x squared minus 2. And since I'm trying to solve for y prime, I have to get rid of everything that's being multiplied by y prime. So I need to divide both sides of the equations by everything inside the parentheses. 8y plus 7 minus 3y squared. 8y plus 7 minus 3y squared, right? If I do it on the left-hand side, I better do it on the right-hand side. That allows me to cancel, and now we're done, right? Now we're left with y prime, which is what we're looking for. Remember, y prime is just the derivative of y with respect to x, dy dx. So it's equal to this 12x minus 3x squared minus 2 over 8y plus 7 minus 3y squared. And that's our derivative that we're looking for. Okay, we did it. All right, that was our first one. Okay, not so bad. So remember the steps here. First, we take the derivative with respect to x, and remember anytime you differentiate a y term, multiply by y prime, or dy dx. Then we move all the y prime terms to one side of the equation and all the non-y prime terms to the other side. Then we factor out y prime and divide to get y prime by itself. Let's try to use that in another example. Okay. So example 3, we're going to find dy dx, find the derivative of the function x squared y squared is equal to 3x plus 5y squared. Okay, so just like before, we start this off by taking the derivative with respect to x on both sides. Okay. Now the right-hand side I know what to do, right? Derivative of 3x would be 3. The derivative of 5y squared would be 10y dy dx, or 10y times y prime. But the left-hand side, oof, this is going to be a little bit tricky. How do we find the derivative of x squared times y squared? Well, you might think, or you might hope that it's maybe 2x times 2y dy dx, or something like that. But unfortunately, this is a product, right? This is x squared times y squared. And because one of your functions is x and the other is y, this means we're going to have to really use the product rule here to take the derivative of the left-hand side. Okay, so before I jump into this, let me do some scratch work. Different color. To find the derivative of x squared y squared. Okay, so remember with product rule, we name one of your functions g and the other one h, and you take the derivative of both sides. Well, I'm not even going to bother to name them. I'm just going to do it as scratch work here. Right, this is my first function, call it g if you like. The derivative with respect to x would be 2x. And this is my second function, y squared. The derivative of this would be 2y times y prime, or times dy dx. Right, if we're taking the derivative with respect to x, then we take the derivative with respect to y and multiply by y prime. Okay, and then the product rule would tell me that the derivative altogether of x squared y squared is going to be x squared times 2y times y prime plus y squared times 2x. Okay, so product rule is giving me this as the left-hand side when I take the derivative. Okay, And now on the right-hand side, we just use the same rules we were using before. The derivative of 3x is 3, and the derivative of 5y squared would be 10y, but we need to multiply it by y prime because we took the derivative with respect to x. Okay, so now that we've taken our derivative on both sides, we need to go ahead and move all of our y prime terms to one side of the equation and everything else to the other side. So I'm going to need to move this term over to the other side of the equation, and I'm going to need to move this term, which does not have a y prime, over to the right-hand side. So when I rewrite this equation, it's going to look like x squared times 2y times y prime minus 10y times y prime, because I moved it over to the left-hand side, and that'll be equal to, I still have a 3 on the right, and then minus y squared times 2x, because I moved this term over to the right-hand side. Change the sign. Now I factor out my y prime term just like before. When I factor the y prime term out on the inside, I'm left with x squared times 2y minus 10y. And on the right-hand side, I still have this 3 minus y squared times 2x. Okay, finally, the last thing that I do is to get y prime by itself, I have to divide by everything inside the parentheses. So divide by x squared times 2y minus 10y. And these cancel, so I'm left with my derivative now. Let's do it in a different color. Y prime is going to be equal to, I'm going to rewrite this. I don't really like having 2's in the middle of my term, so I'm just going to bring the coefficients out in front. And I can rewrite this as 3 minus 2 y squared x. Right, that's this term, just moving the 2 in front. Divided by, again, I'm going to move the coefficient in front, 2 x squared y minus 10y. That's my derivative. Okay, right, so the tricky part here was recognizing that because we had a term with both x's and y's, we needed to use the product rule to take the derivative of that with respect to x. So let's try to do that with one last example here. We're going to find the equation of the line tangent to this particular curve at the point 1, 0. Now, it's always a good idea to double check and make sure that this point actually makes sense for this particular curve. In other words, if you plug in 1 for x and you plug in 0 for y, you should get something that's true. And you do, right? This would be 1 squared plus 0 squared minus 1 times 0. So 1 plus 0 minus 0, that's 1 on the left. And on the right, you should end up with 5 times 0 plus 1 cubed. 0 plus 1 is 1. Great. So 1 does equal 1, which means this point is indeed on this curve. And so to find the equation to the tangent line, we need a point on the curve, which we have, 1, 0, and we need a slope. Right? Well, to find the slope of the tangent line, we need to take the derivative. So we take the derivative with respect to x on both sides. d dx of both sides. Okay, now, just like before, it's going to help me if I start off by doing a little bit of scratch work for any term that involves both an x and a y. If it involves both an x and a y, you're going to have to use the product rule. All right, the only term that has x's and y's is this negative xy term. So I'm going to split this up into negative x and then y, right? For the product rule, those are my two different parts, the negative x part and the y part, and I take the derivative of both to apply the product rule. The derivative of negative x is just negative 1, and the derivative of y is just 1, but we need to multiply it by y prime. Okay, and so then we would use the product rule to take this derivative. All right, so let's go through now and find the derivative of everything else and put it together in one big equation. We're going to get the derivative of x squared is 2x plus the derivative of y squared would be 2y times y prime. Right? Anytime you take the derivative of a y term, multiply by y prime. And then the derivative of negative xy using the product rule would be negative x times y prime. And then plus negative 1 times y. Well, we're adding a negative y. Okay, that's the left-hand side. And on the right-hand side, if I take the derivative of y prime, I would get 5 times y prime. Derivative of 5y is just 5, then multiply by y prime. And the derivative of 3x squared is, the derivative of x cubed is 3x squared. Okay, the next step is to move all the y prime terms to one side and everything else to the other. So 5y prime is going to have to move to the right-hand side, and then 2x and negative y are going to have to move to the other side. I think I said that wrong, but right. All the y prime terms on the left, everything else on the right. And when I move everything over, I'm going to be left with, let's see, 2y times y prime minus xy prime. And then this 5y prime needs to move over by subtracting it, so we have a negative 5y prime. And on the right-hand side, we have 3x squared. Then we have, let's see, 2x needs to move over, so we'll have a negative 2x. And negative y needs to move over, so we would add y to both sides and end up with a positive y on the right. Now factor out your y prime. You're left with 2y minus x minus 5 inside your parentheses is equal to 3x squared minus 2x plus y. And to get y prime by itself, we divide by everything inside the parentheses. So divide both sides by 2y minus x minus 5. And there we have our derivative. Our derivative y prime is equal to 3x squared minus 2x plus y, all divided by 2y minus x minus 5. Great. Now, is that what they asked for? No. They asked us for the equation of the tangent line, not just for the derivative. Okay, so remember, to write the equation of the tangent line, we need two things. We need a point on the line, which they gave us already. That's the point 1, 0. And then we need the slope of the tangent line. But remember, the slope of the tangent line is the derivative. In fact, it's the derivative evaluated at the particular point 1, 0. So we need y prime evaluated at 1, 0. I'm just going to write this meaning to evaluate y prime at 1, 0. So we plug in 1 for x's, and we plug in zeros for the y's, and see what we get. So plugging them in using this equation for y prime is going to give us 3 times 1 squared minus 2 times 1 plus y, which is 0, divided by 2 times y, that's 2 times 0, minus x, which is 1, minus 5. All right, now I simplify this. 3 minus 2 plus 0 over 0 minus 1 minus 5. 3 minus 2 would be 1 over negative 6. There's our slope. Now that I have a point on the tangent line and the slope of the tangent line, I just plug everything in using slope-intercept form. So it's y minus 0 equals negative 1/6 times x minus 1. And there's our equation. That's what we were looking for.